Hello everyone. Let's review the application of the Fourier transform. If we have an input x of t going to this system with impulse response h of t, then it will give us this output y of t. And we can find y of t as the convolution in the time domain between x of t and h of t. In the Fourier transform, we define the Fourier transform with this integral. If I have the signal in the time domain x of t and I need to find its Fourier transform or the frequency, it's the signal x of t times the sinusoidal integrated from minus infinity to infinity. So by taking the Fourier transform of the signal x of t using this definition, I get the frequency of the signal x of t, which is x of omega. If I apply the same thing, the Fourier transform of f of t, we will get the frequency response, h of omega. Now to find the output y of omega is just the multiplication of h of omega and x of omega. If I want to hear or see the output in the time domain, y of t, I do the inverse Fourier transform of the spectrum of the output. So you just do the inverse Fourier transform of the output y of omega, you will get the output in the time domain. And one application of these, if I have the input x of t here going to the system, which is just a white noise like shh, and it has many frequency component. If I do the Fourier transform of this signal, I get x of omega, which has many frequency component. And I take this input x of t to the system h of t that has a Fourier transform or a frequency response, which is this one. Basically what it does, it amplify the 700 hertz, 1200 hertz and 2300 hertz. Now the output will be just this frequency response h of omega times x of omega. So when you multiply these by these, that's what you will get. And these will sound like oh, the vowel. So you can create a machine talking just by exciting a system like this one and excited with white noise that has all frequency component. The output of the system will be the sound of oh, but it will be more like a machine sound. And these mimic exactly the vocal system we have. It's just like a mechanical system. You have the vocal cord, you have the air tube, you have your tongue, your lips, your teeth. So you move them mechanically and you fix them in a certain way, and the air buff comes. Now, the way you fix your tongue, your lips, it's a mechanical system with a frequency response this. So it has a resonance. The resonance will be this frequency, 700, 1200, 2300. That will be amplified. And all other frequency present here will be attenuated. Only the 700, the 1200 and the 2300 will be amplified, and which will generate that sound. And for the letter E, you will have a different system with different resonance frequency. For the different type of vowel like hid, hide, had, hood, for the O, these are the frequency, the dominant frequency. This is around 700, this is around 1200, this is around like 2300. The I, these are the frequency resonant, or they call them the formant. So as you shape your vocal cord, your mouth, mechanical system, it will have a different resonance frequency. And for female and children, because their vocal cord and those are smaller, they will produce sharper tone. So the O sound for a female and a child, it will be the same ratio. It's just going to be all shifted up. So this will appear here. This one will be shifted up. This one shifted up. So what makes these O different than A is the different frequency and the distance between them. Now the question is, how do we create a system that looks like this, that will amplify the 700, the 1200 and so forth? Well, we can use the pole zeros technique. Okay, so let's go back and do some examples. So we need to find the inverse Fourier transform of this delta function. So I have x of omega an impulse located at omega 0. Now we know in real life, we always said the magnitude of x of omega, or the spectra amplitude of a signal, always even. So we should expect 1 here, but we don't have. The problem didn't have it. Let's see what will happen. So we just want to find the Fourier transform of this. So we will do the inverse. So if this is x of omega, then x of t will be 1 over 2 pi, the integral of delta omega minus omega 0, ej omega d omega. And that would be 1 over 2 pi. An impulse multiplied by a function is just like sampling this function at the location of the impulse. This impulse located at omega 0. Ej omega, plug for omega, omega 0, the location of the impulse, d omega. And now ej omega 0 t has nothing to do with d omega, the variable, so it comes outside the integral. So that will be what's the integral of an impulse? Is 1. And that's the answer. So ej omega 0 t in the time domain over 2 pi, the Fourier transform is this impulse. So we are giving this impulse, and we found the inverse Fourier transform this. If I multiply by the 2 pi, then I will get ej omega 0 t, multiply both sides by 2 pi delta omega minus omega 0, which is this property. Now, in real life, we cannot generate this complex number, ej. And that's why when you were giving x of omega only that impulse, and mathematically you can carry out the operation, but in real life, the magnitude x of omega is even. But we're going to use this property to find the Fourier transform of a cosine function, which is very important function. We will have many applications. So instead of carrying out the Fourier transform integral, I will express cosine omega 0 t in terms of exponential. So that will be half using the trigonometric. The Fourier transform of this one is the same as the Fourier transform of this one. So when I do the Fourier transform for this one, the half will come out. The Fourier transform of this component, we just found it here in the top here. It's just 2 pi delta omega minus omega 0. The Fourier transform of this one is the same as this one, except with instead of omega 0, it's minus omega 0. So, and you will get plus 2 pi delta omega minus omega 0. And the 2 will cancel with the 2 pi with the 2 pi, and the Fourier transform of cosine omega 0 t. And that's exactly this answer. And we will see a big application for this and later on in communication. Let's take another example. So in this example, find the Fourier transform of this signal. Now, when you look at this signal, I am sure you will recognize it and say, oh, this looks like the exponential Fourier series of a periodic signal with harmonics n omega 0. So our omega is not anymore continuous like Fourier transform. This signal x of t is a periodic, and it has only discrete frequency, harmonics. It has a DC, omega 0, 2 omega 0, 3, 4, 5, 6, and 7, and so forth. And each harmonic will have this strength, dn. So the fifth harmonic, 5 omega 0, its strength will be d5. But you are given this problem and you were asked to find the Fourier transform of x of t. No problem. Apply the definition. So x of omega will be the Fourier transform of the signal. Summation is a summation, so it will come out. dn is a constant. Now here, this is your function, ejn omega 0 t. This is the function that we need to find the Fourier transform. That's not problem because we already did. We found it here. The Fourier transform of an exponential is just 2 pi time an impulse at the location of the omega 0 here. So that means the Fourier transform of this will be just a delta omega minus n omega 0. And that's x of omega. This is the Fourier transform of this periodic signal. And if you plot x of omega, the magnitude, when n is 0, that's the DC, you get d0. So that will be just 2 pi d0. When n is 1, you get an impulse at omega 0. What's the strength of it? It's 2 pi d1. When n is 2, that's the second harmonic. It may be larger or smaller, depend on n. And so forth, and this is d minus 1, d minus 2. So the Fourier transform here exactly telling us this periodic signal only has discrete. It has a DC, first harmonic 6. It doesn't have any more like this, x of omega, something like this, continuous. So Fourier transform is a general. It can find a spectrum of a periodic or non-periodic signal. For a periodic, it will be discrete. For non-periodic, it will be the spectrum continuous. Now, if you are giving a unit impulse response, and this is a very important function, they use it for sampling. So it looks like this, T0, 2T0. If I have a continuous signal, I want to sample it, I will multiply it by this train of impulses, and it will take a sample every T0 of the signal. So if T0 is 1 millisecond, that means you're going to take 1,000 samples per second. If T0 is microsecond, then you will take 1 million samples every second. So this is the train of impulse. And I need to find what's the Fourier transform. Well, in Fourier series analysis, this is a periodic signal, and we found the exponential representation of a periodic train of impulse. And we found it to be this one. If I call this x of t, and I need to find the Fourier transform, again, using the example we did before, this is the function in the time domain, and the Fourier transform of it is 2 pi time an impulse at the location. So the Fourier transform of this will be this one times the 2 pi. 1 over T0 is constant, and the summation will be here. And if you plot this, x of omega, then you will have a train of impulses every omega 0 to omega 0, and so forth. And the amplitude is 2 pi over T0. We demonstrate how to use the Fourier transform and the inverse Fourier transform for several functions. You have a table here of common function x of t and their corresponding Fourier transform. More function here. This is a continuous, so another functions here that will find the Fourier transform in this. Next is the property of the Fourier transform, and they are similar to the property of the Laplace. The first is linearity. If you have a signal x of t and you have the Fourier transform x of omega, another signal y of t and y of omega. Now, if I add these two signals in the time domain, x of t and y of t, and multiply each one of them by a scalar like alpha x of t, beta y of t, then the Fourier transform of this new signal will be just x of omega times alpha plus y of omega times beta. Linearity, we use it when we have a linear system, and if the input consists of 34 components and you know the system responds to each component, just add the output of each component, and that will be the response for all components added together. Now the duality is just from the definition. The Fourier transform of a signal x of t is defined by this. The signal in the time domain, you can find it from its Fourier transform by carrying out this integration. So this is the Fourier transform, this is the inverse Fourier transform. If you replace t by omega, and here minus omega plus j omega, and this is a factor, these two integration, they look very similar. So the duality says the following. If you have a signal x of t and the Fourier transform is x of omega, then if I create a signal in the time domain that has the same shape as this, so omega I just replace it by t, so now this is a signal in the time domain, then the Fourier transform of this signal will be exactly this shape, except you replace t by minus omega and you multiply by 2 pi. So how do we use this duality? You can solve problems like if I give you this sinc function in the time domain and I ask you to find the Fourier transform. If you carry out this integration, it's a little bit long. Or you recognize from the table, if you have a rectangular in the time domain, then its spectrum is a sinc function. So now you have actually the sink in the time domain, and you need the Fourier transform. We're going to use this property. So first, I will rewrite these as follow. I will divide by tau here and divide by tau here. So I get, now I will use the duality. If I create a signal in the time domain that looks the same shape, except I replace omega by t, so then I get sinc tau over 2, I replace omega by t. So now the Fourier transform of this one will be 2 pi, the inverse Fourier transform of this, x, which is this one, that's x of t, except with t I replace by minus omega. So that means I will get 1 over tau, a rectangular, instead of t I replace minus omega tau. And this is, and that's the Fourier transform of this sinc function. It's this one. And that's the solution without carrying out this integral. Now the rectangular here, minus omega, omega, this rectangular here is the same as rectangular omega over tau. This is just a special case, because if I rotate this around this vertical axis, I will get the same pulse. Let's continue with the property. Here the time scaling. So if I have a signal x of t and the Fourier transform is x of omega, now if I compress the signal in the time domain, omega over a here. So compression in the time domain is expansion in the frequency domain. Same thing, if I expand the signal in the time domain, it will be compression in the frequency domain. And there is here 1 over a. If you carry out the proof, you will see where this 1 over a is. But intuitively, you can see that. If I told you you have transmission channel that transmit 1,000 pulse per second. So that is this first channel. So that means every 1 millisecond you send a pulse. That means the pulse has to be 1 millisecond or less. Now there is a channel that transmits 2,000 pulse per second. So if it has to transmit 2,000 pulse per second, the width of the pulse has to be very small. So it can squeeze 2,000 of them in 1 second. See, if I compare these two in the time domain, the width here is twice this. So that means I compress to come from here to here. I compress the signal by a factor of 2. What happened in the frequency domain? You expand the channel bandwidth from 1,000 to 2,000. You expand it by a factor of 2. And that's the impact. And we can expect this. If I give you a signal like this in the time domain, and it has a frequency, let's say up to 2,000 hertz. Now, if I compress this signal, it will fluctuate a lot now in a small period of time. And fluctuation means it contains high frequencies. So that means the spectrum of this one now, instead of just 2,000, now probably it will be 4,000. So in the time domain, you compress it. In the frequency domain, you expand it. And that's the property of time scaling. Time reversal, if you have x of t and x of omega, now if I rotate the signal around the vertical axis, I rotate the spectrum around omega. And to solve this, for example, if you want to find the Fourier transform of this function, I can express this e minus a t as. So if I plot this one, if I call this x of t, so if I plot it, it will look something like this. This one here describe this portion. This one here describe this portion. Now the Fourier transform of this signal using linearity is equal the Fourier transform of this one, and we already have that one in the table. It's just 1 over a plus j omega, and the Fourier transform of this one is just 1 over a minus j omega. If I add them up, it will be a squared plus omega squared 2a. Now time shifting property says the following. If you have a signal x of t and that's the spectrum x of omega, if you do time shifting in the time domain, it's equivalent to phase shifting in the frequency domain. to see it intuitively, if I have a signal cosine omega t, now I shift it. So now t minus t0. So if this is x of t, this is x of t minus t0. And this will be cosine omega 0 t minus omega 0 t0. And that's the phase shift, which is this. So if I have this example, I need to find the Fourier transform of this one. Well, in the previous example, we found the Fourier transform of these 2a over a squared plus omega squared. So now this signal here is the same as this signal is shifted. So then the Fourier transform of this one will be exactly x of omega, which is this, multiply by the phase shift, e minus j omega t0. It's shifted by that amount. It could be 1 millisecond. You put 1 millisecond here. I am skipping the proof because we did in the Laplace, but let's show you that it's not that difficult to show the proof. If I ask you find the Fourier transform of the signal x of t minus t0, the definition will be x of t minus t0 times e minus j omega t dt from minus infinity to infinity. If I do u substitution by letting u equal t minus t0, then du will equal dt. Also t will equal u plus t0 from here to here. Okay, so let's do the u substitution. So when t go to minus infinity, u will go minus infinity minus t0 is minus infinity. When t goes to infinity, t0 is small, so that's also will go to infinity. X, replace t minus t0 by u, e minus j omega, replace t by here, u plus t0, dt is du. Now e minus j omega time t0 has nothing to do with u, so it will comes out. And this will be x of u e minus j omega u du. Now when you look at this one, that's the Fourier transform of a function x. It doesn't matter if it's u or t or tau or v, that's a random variable. But that looks like the definition of a Fourier transform of a function x. So this is exactly e minus j omega t0 x of omega. And that's this. So when you shift the signal in the time domain, it's phase shift in the frequency domain. And that's the proof. So I'm skipping the proof. It's just similar proof like this. You can carry it out in the textbook. It's 2-3 lines in detail. Let's continue with property of the Fourier transform. So the next one is differentiation in the frequency domain. So if I have a signal x of t and I have the Fourier transform x of omega, if you multiply the signal by t of n in the time domain, in the frequency domain, it will be the n derivative of x of omega, time phase j n. So if I want to know what is the derivative of the spectrum of a signal multiplied in the time domain, if I need the first derivative, multiply it in the time domain by t to the power of 1 and take the Fourier transform. That will give you the derivative of the original signal. And derivative usually tell us how fast does the signal fluctuate, how rapidly does it change in time or in frequency. And there are other applications for it. Another property that we use it a lot in system analysis, just like in Laplace, is the differentiation in the time domain. So if this is x of t and that's the spectrum, the Fourier transform x of omega, if I take the n derivative of x of t, it's like you take the original spectrum x of omega and you multiply it by j omega to the power of n. Just similar to the Laplace property, you multiply it by Sn x of s, where s is just j omega in the Fourier transform. And we use this property when we convert a differential equation from the time domain to the Laplace domain, or in the frequency domain it will be j omega to the power of n x of omega plus and so forth. To practice with this one, we have a function here we solved in the Laplace domain, and it's similar. So you have a delta function with tau, so this is tau over 2, this is minus tau over 2. And we need to find x of omega. One way is just to carry out the integration. Other way is use property. So if I take the derivative of this one, it will be, this is a RAM, so the derivative will be this one. This is a RAM with a negative slope, so it's going to look something like this. I'm not going to go in the detail of the solution because we solve it in the Laplace domain. It's in the textbook. So this is dx of t dt. You do a second derivative of this one, you will get an impulse here. This is a DC. Derivative of a DC is 0. Then you have another drop change, so that's an impulse. DC 0, then up, so that will be here. And this is d square x dt square. So you find the Fourier transform of this one. That's very simple, just impulses. And the Fourier transform of this one is very simple. It's use this property. So that would be j omega to the power of 2 x of omega. And you find the Fourier transform of this and you equate it to this one. You divide the Fourier transform of this you found by j omega to the power of 2, which is just minus omega square, and you will get x of omega, which is the Fourier transform of this one. Let's look at the next property, which is integration in the time domain. Same thing in the Laplace domain. When you have x of t and it's x of s, you integrate these, then it's equivalent to x of s divided by s. And the same thing here, and plus some initial conditions. This is 1 over s. The frequency domain is just j omega because sigma is 0. The next one is convolution, which is another important property. We use it in system analysis. So if I have x of t, and that's the Fourier transform x of omega, and another signal y of t, and the Fourier transform is y of omega. If I convolve these two signals in the time domain, in the frequency domain, it's just a simple multiplication. X of omega times y of omega. If I do duality, a multiplication in the time domain of x1 of t and x2 of t, in the frequency domain is just a convolution, divided by 2 pi. We use this property for system analysis because remember the system analysis, if you have h of t and you have an input x of t and you get y of t, so y of t is just a convolution of x of t, h of t. In the frequency domain, y of omega, a convolution is here. So a convolution of these two, x of t with h of t, is just a multiplication. So that y of omega will be just x of omega, h of omega. In this example, you have x of t and you have h of t. So basically, you have x of t here is e minus a of t. So x of omega, if I use the table, it's 1 over a plus j omega. And the system impulse response, so h of omega is 1 over b plus j omega. Y of omega will be x of omega times h of omega. So that would be, that's y of omega. Now, if I need to find y of t, because in the problem said find the system response to the input, so we need to find y of t, not y of omega. So you have two options. One option is do the inverse Fourier transform of this signal and carry out the integration, which is a little bit long, or use partial fraction expansion. So we can express y of omega as c1 over a plus j omega plus c2 over b plus j omega. So I do partial fraction expansion of this term. When you do partial fraction expansion of these terms, C1, C2, and you have to find C1 and C2 using the same technique we did before. Just to show you how do we find C1, this we said is equal exactly this. And if I need to find C1, I multiply both sides by a plus j omega and set j omega to equal minus a. So C1 will be, if I multiply this term by a plus j omega and I set j omega minus a, this will go to 0. I multiply this by a j omega, this will end up with b plus j omega. Then I set j omega equal minus a. When I multiply this term by a plus j omega, I get C1. And this will be 1 over b minus a. And same thing here, C2, if you do the same thing to find C2, you multiply every component by b plus j omega and you set j omega to equal minus b. And you will end up with a minus b. And then y of t will be, C1 is a constant, 1 over a plus j omega is e minus at u of t from the table. C2 is a constant, 1 over b plus j omega, the inverse Fourier transform is e minus b t u of t. And C1 we found it to be this term, and C2 we found it to be this term. Still, this is much easier than carrying out the convolution of x of t with h of t in the time domain. I will stop here and in the next lecture explain amplitude modulation property and the big application of modulation in communication.